Development and control of a quadruped robot via SolidWorks and MATLAB's Simulink modeling. Welcome to the simulation of our quadruped robot project. In this video, we present the modeling, control strategy, and gait validation using MATLAB and Simulink. After completing the CAD design of the quadruped robot in SolidWorks, the first step was to migrate the model to MATLAB using Simscape Multibody. After the import process, each part of the robot is represented by a corresponding block in Simulink, complete with its mechanical and physical properties. Here we present an overview of the imported blocks for each leg. Each leg has 3 degrees of freedom, totaling 12 DOF across the quadruped. The servo motors control the movement through revolute joints, which receive angle commands. These joints apply angular and torque limitations based on the specifications of the physical SG90 servos. The resulting motion is visualized along the y-axis in the Mechanics Explorer during simulation. This simulation environment enables us to evaluate the forces and torques acting on the robot, such as inertia, friction, gravity, and others, which are crucial for accurate physical implementation. Each revolute joint provides 3 essential output signals for robot analysis: position, velocity, and acceleration. Additional joints are employed to ensure that the multiple elements of this complex mechanical chain perform cohesive and stable movements. To reduce computational load during simulation, each leg includes a 5 mm sphere at the tip to represent the contact point with the ground, which is used later in the analysis of the center of mass. All 4 legs follow the same structural block configuration, ensuring symmetry and modularity across the robot's design. In the thigh joints, we configured the physical limitations of the SG90 servo motors by defining their minimum and maximum rotation angles directly in MATLAB. As mentioned previously, small spheres placed inside the tibias, or feet, are used to detect ground contact. This is achieved through the spatial contact force block. The default stiffness and damping values provided by Simscape are used as they are suitable for this type of robotic simulation. The contact output signal is processed through a reshape block, which converts the contact signal array into a format suitable for further analysis, particularly for determining the center of mass. Additionally, transform sensor blocks are used to measure the XYZ translation of each leg. These 3x3 matrices are also reshaped and processed for use in later evaluations. A flat rectangular block measuring 2x10 by 0.005 meters was used as the ground plane for the robot's movement. This ground was offset by 11 centimeters along the z-axis, using a rigid transform to correctly align with the robot. The robot's main body connects all 4 legs and serves as the interface between the robot and the simulation world. It is attached to the global reference frame using a 6 degree of freedom joint, which allows all possible degrees of freedom for motion. Within this subsystem, an inertia sensor block is used to capture the robot's mass properties in center of mass. These values are output as 3D vectors, processed through a reshape block, and stored in the MATLAB workspace for further analysis. All the previously mentioned blocks were grouped into a single subsystem, renamed as Robot. This subsystem receives as inputs the joint angles for the 12 revolute joints and provides as outputs the position, velocity, and acceleration readings from each joint sensor. Scopes were used to monitor and analyze the time response of these variables throughout the simulation. Specifically, the joint position signals are fed back into the robot control subsystem, closing the loop and enabling dynamic interaction between the simulated controller and the mechanical system. The robot's control system starts with a decimation clock of 10, which makes the simulation run from time. The leg trajectory is generated using a parameterized function that defines the foot's motion in 3 dimensions over time. The function takes into account the total gait cycle duration, the individual leg phase offset, the step length, and the desired step height. The trajectory is divided into 2 main phases: stance and swing. During the stance phase, the foot moves linearly backward along the x-axis, simulating propulsion while maintaining contact with the ground. In the swing phase, the foot moves forward while lifting smoothly in the z-axis, following a sinusoidal profile to ensure ground clearance. The Y position of the foot remains constant, corresponding to the lateral position of the leg on the robot's body. The entire motion is time normalized within the gait cycle and adjusted by a phase parameter, enabling synchronized and coordinated movement across all 4 legs. For simulation purposes, we used a diagonal crawl gait with a custom phase sequence of 0.00, 0.50, 0.25, and 0.75, corresponding to the FR to BR to FL to BL activation order. This differs from the sequence proposed in the reference paper and was chosen to demonstrate the flexibility of the gait generation method. The output of the trajectory generation block consists of the desired foot position in Cartesian coordinates, px, py, and pz, which are continuously updated for each leg throughout the gait cycle. These coordinates serve as direct input to the inverse kinematics module, which computes the joint angles required to position the leg accordingly. For each leg, the inverse kinematics algorithm is responsible for solving 3 rotational angles: theta, coxa, theta, femur, and theta tibia, corresponding to the hip yaw, hip pitch, and knee joints, respectively. The solution begins by calculating the coxa rotation angle using the arctangent of the lateral and frontal positions. Then the position is translated into the coordinate system of the femur joint, and the total distance to the foot is computed. The algorithm applies geometric methods, including the law of cosinus, to determine the tibia angle. Subsequently, the femur angle is calculated using the orientation of the leg in the sagittal plane, adjusted for mechanical offsets. This process ensures that, at each instant, the foot follows the planned path accurately, while the corresponding joint angles remain within the robot's mechanical limits. The joint angles computed by the inverse kinematics block, theta coxae, theta femur, and theta tibia, represent the target positions for each actuator in the leg. These values are continuously updated during the simulation and transmitted to the robot's control system. In a real implementation, these angles would be converted into motor commands and sent to the respective joints via low-level controllers, such as PID loops. This feedback process ensures that the robot tracks the planned gait trajectory accurately, allowing coordinated and stable movement across all 4 legs. In simulation, these joint angles are used to animate the robot model in real time, enabling the evaluation of gait stability, workspace constraints, and dynamic consistency before physical deployment. To monitor the performance of the inverse kinematics in real time, each joint angle is visualized using dedicated scopes for each leg. This allows for individual analysis of the angular trajectories throughout the gait cycle. By observing these plots, it is possible to verify the smoothness and continuity of the joint motion, detect any abrupt transitions or inconsistencies, and confirm that the generated motion remains within feasible joint limits. This step is essential for validating both the gait timing and the inverse kinematics implementation before applying it to the physical robot. The simulation used the ODE force solver with a fixed step size of 0.0001. In this section, we present the simulation of the quadruped robot executing a crawl gait. As previously described, the gait uses a diagonal leg activation sequence with phase offsets of 0, 0.50, 0.25, and 0.75, corresponding to the order FR to BR to FL to BL. This variation from the standard gait presented in the reference paper was intentionally selected to demonstrate the flexibility of the trajectory generation framework. Throughout the 18-second simulation, the joint angles calculated by the inverse kinematics are continuously applied to the robot model, allowing it to execute 3 complete walking cycles. The gait is carefully synchronized across all legs, ensuring that at most one leg is in the swing phase at any given moment, a defining feature of the crawl gait that enhances static stability. Multiple camera perspectives are used in the simulation to visualize the robot's motion from different viewpoints, including side, top, and isometric views. These perspectives highlight the coordinated movement of the legs, the tracking of the planned foot trajectory, and the overall body stability during locomotion. The slow and deliberate leg transitions allow for better weight distribution and a wider support polygon at all times, minimizing the risk of tipping or instability. This gait is especially suitable for low-speed navigation in uneven terrains or when the robot must maintain balance in response to external disturbances. The smooth progression of the legs, together with the real-time visualization of joint angles via scopes, confirms the consistency of the inverse kinematics and trajectory generation blocks. This simulation phase is crucial to validate the algorithmic design before deploying the control strategies to a real hardware platform. This concludes our simulation overview. The physical quadruped robot has already been assembled, and the implementation strategies are currently in full progress. Future work includes testing the control algorithms on the real hardware and validating the simulated results in real-world conditions. Thank you for watching.